What's up, Will? All right, so we already went over a couple things about the manipulating equations homework. The only thing you need to know about that is that I pushed the due date back a day, so it's due tomorrow. Nothing else is pushed back, though. So that means both the manipulating equations and linear equations worksheet, linear regression worksheet is due tomorrow. Oh, what I didn't tell you. This morning for the linear regressions worksheet to help you out, I made an answer key a little bit for that. It's not quite an answer key because it doesn't do everything for you. It doesn't show you all the answers, but it kind of gives you hints on like where you're screwing, maybe doing it right or screwing up. The other thing I want to say is this. In linear regression, when you go to labs, the idea, if we combine everything together, is this. I give you an equation. You go out to the lab, okay? And if the equation is correct, everything you get out there should ideally match with what we said on the equation. That doesn't always happen, okay? Now, usually at this level of physics, it's probably because you made some sort of mistake. But ideally at the high level of physics, if you did something perfect, if the real life doesn't match the equation, which one should we probably trust more? What's that? Real life. Right. Forget your equation, Spanauer. This is what life says. Why are we worried about that? So if you did everything perfect. So point being, there is a problem on that worksheet where things don't match, and that is correct. I don't want you to like kind of be confused, like, what did I do wrong? Okay, it's it kind of walks you through the steps. If you just read what it says to do, it tells you what to do next. Okay, but on that problem, it was the one I told you I was going to take off yesterday, and as I read through it, I was like, oh no, I don't want to take that off. That's pretty good. But it kind of tells you what to do next, what to do next, what to do next. Anyway, that is certainly the case. So today we are going to get into what are known as the kinematic equations. Now, the kinematic equations are just the equations that, kind of wrap up all of these ideas of kinematics within them. And actually, we already have one of them, okay? Well, we actually have two, but you'll see how they kind of wrap up into the total. For starters, we have average velocity. What is the other equation definition that we have right now? Acceleration. Acceleration. Oops, there we are. With these two ideas, as addition to one other thought, we're going to make some kind of complicated equations a little bit later on, but they should make sense, which leads me to this. We should probably briefly go over what your results should be on the lab if you're doing it correctly. I asked you to graph them for today. If you haven't, it's okay, but let's make sure that you're good on that. So the first graph, even if you don't have it done, get this down so you can check yourself. Okay, we talked about this one yesterday. The first graph should make what shape? Yep, parabolic. Okay. The second graph, average velocity versus time, should make what shape? Linear. Correct? If you've done it correct. This next one is where people screw up, and I talked a lot about it the other day, but if you did it wrong, that's okay. Just redo it. Instantaneous versus time should be linear. If you made a mistake, you got a hyperbolic function. You should not get a hyperbolic function on this graph. If you got a hyperbolic function, it's because you used the wrong time. I told you we are never using time flag on these graphs. This should still be the exact. Let's put it like this, guys. You'll notice that these first three graphs, time is on the x-axis. Ideally, that scale is exactly the same for the first three. Yay, hooray, we don't need to change much of anything. The final graph has the same y-axis as the previous one, but switches over to delta x. And what shape should that be if you've done it correctly? That's a square root, correct. So as we are done, just talking about, again, what you're going to be needing to do, those two, you can immediately go into finding the equation of the line. Make sure you're using the appropriate symbols as well as units in that spot. The top one and the bottom one are, of course, going to require a linear regression in order to get those constants to go back. So in total, like I said yesterday, you're going to have about 6 graphs. But that's probably going to come into play today. Let's come back over here. The first kinematic equation that you sort of already have is kind of up there. And that is for what if things have a constant velocity? Well, we've discussed this. If it has a constant velocity, then that's going to be the exact same as the average. Yes? Meaning, if my velocity stays at 7, at 7, at 7, at 7, at 7, and I added up all those 5 7s I just said and divided by 5, obviously the average will be 7. Yes? Meaning that a constant velocity has the exact same equation as the average. Now, I'll tell you the truth, this is such a basic equation that usually I want you to start at a very specific spot. This one, quite frankly, I don't care. Okay, you can start here or do one step of algebra and always start here. I don't care. I really don't. Now, I don't want you to start at the time one. That's not a usual starting spot. But I did want to point this out real quick. Did you guys ever do distance equals rate times time problems in like elementary or junior high or somewhere along that line's coming up? Distance equals rate times time. That's all this equation really is. Displacement equals velocity times time. All right, next. So that's if it's a constant velocity. That's the only equation for constant velocity. The 3 kinematic variables that go into constant velocity are the 3 you see here, delta x, v, and delta t. So beyond this point, giant line, what we are going to tackle from here on is what if there is an acceleration? So up here, acceleration is, remember, 0. Because a 0 acceleration means velocity is not changing. So constant velocity, 0 acceleration, say the same thing. And down here, acceleration is anything but 0. The kinematic equations, by the way, rely on I'm going to ask you this a ton this year. Like, what is the basic assumption of the kinematic equations? The basic assumption of the kinematic equations we actually stated the other day when I put up jerk and snap and crackle and pop up there, and it's this. We're not worrying about those, which means in this class, acceleration is always constant. Okay? If it changes, we say it changes immediately. It switches on immediately. In truth, that's really, really close to accurate. Okay? But not quite perfect. So again, to make the kinematic equations that you see below here, we assume acceleration is constant. So that could be, by the way, and when I say constant, that's either a constant 0 or constant 7 or 6 or whatever. Now again, we will allow acceleration to change, but when it changes, we're going to say it changes immediately from 7 to 0. Immediately. Does that make sense? Okay. The good news with the first one is it's just a rearrangement. By the way, we have a lot of algebra today. And when there's a lot of algebra, I cannot stress this enough. Do the algebra. Do not take pictures. Write it down. As a matter of fact, you might even copy it later. To put this in perspective, guys, I've done this for a minute, and I do this algebra every single year to prep for this, just to make sure that I have moves and that type of thing. So here. This is basically the equation. This is the second equation, but we're going to do some rearrangement for purposes. I'm going to multiply t on both sides. And here, I want to stop and point this out real quick. Okay, so any move I make up here, or any kind of like equation I put up here, I suggest you do the same. Don't forget that this is actually just this, right? Yes? So what is the change in velocity? What is the change in anything? How do you get the change in anything? So notice when I wrote this equation, what this says is that this left side is the change in velocity, as is the right side. Why is that the change in velocity? Well, look, if I took A, which is the change in velocity over time, and multiplied by time, what would I be left with? Change in velocity. So when you see this, the hope of stopping at this point is when you see this, I hope you still see the change in velocity. One more easy move is add VI on both sides, and right here is your first kinematic equation. And that equation is simple in that you should understand what it means. What does this simply mean? Hey, if I start with an initial velocity and I add how much it changes, I should know what it is at the end. Simple stuff. If I start going 2 and my velocity changes by 4, then I get 6. That's all it is. Except the change, there's a few other steps. Like acceleration, I might have that acceleration. Let's change my number slightly here. So acceleration is 3 meters per second squared. Hopefully, when I write that number, what you actually see is it's going to change by 3 meters per second every 1 second. So if it changes for 2 seconds, it will change by a total of 6. Good there? So if I started at 2, add 6, of course I should end at 8. Now, moving on. Let's talk about average velocity for a second, because I did a whole lesson, and I've done this video already, so I'm not going to do a ton of time, especially for those of you who've seen the video, but it's not bad to hear it again either. There was a problem that we did in here where I walked across the front of the room, I think 1 was 3 and 1 was 1. I told you can't just take 3 and add 1 and divide by 2. We remember this, yes? Okay. Do you remember the reasoning of why? Yes, and I'm going to change that slightly, because that's not wrong. But what are we actually averaging? What we're actually averaging is the instantaneous velocities, right? If I add up all the instantaneous velocities of me going 3, and then all the instantaneous velocities of me going 1, were there more of me going 1? Yes, because of the reason you just stated. So if I can add up all those 1s and add up all those 3s and divide by the total number, I should get less than 2. I should get less because it's not even. But along those lines, excuse me, if I do have the same amount on either side, I should be allowed to use that. One thing that I think helps on this front, let's actually go to another page quick, is a graph. So in my first example, I said, hey, Spainhour starts at 3 for about 1.33 seconds, and then drops down to 1 for, I believe it was another 4 seconds. You'll notice I put 5.33, just adding 4 to the first one. Okay. So if I try to look at the average here of taking 3 plus 1 divided by 2, hopefully you can very clearly see that it's not evenly split between the two, so that red line doesn't work. Does that make sense? On the other hand, if acceleration, as we just said, is constant, that means there's always a constant change in velocity. So let's pick some different numbers real quick. Let's say instead I started off at a speed of 1 here, okay? And I speed up to 3. This is Spainhour's already walking, and he accelerates to 3. That would take time. And it would go like that, because it would be a constant change. Now, are half of the velocities above that red line and half the velocities below that red line? Yes. Or is there the same amount of time above it as below it? Yes. So with a constant acceleration, which we are assuming, is it okay then to use that average velocity equation that we've done previously? Yes. What would you call this guy right here? It's accelerating. What do you call 1 meter per second? Velocity initial. That would be velocity initial. And 3 meters per second would be, so to give an equation for average velocity, that would simply be average velocity in this case is VI plus VF divided by 2. Yes? So coming back here, I should be able to take this equation and say average velocity is equal to delta x over delta t, which it is, but is now also, in these conditions, equal to VI plus VF over 2. And doing a little bit of a rearrangement, let's forget this guy and just focus on everything over here. I don't want to put a box around it because that's not the final equation, but focus on everything over here. I'm going to multiply both sides by time, and I get that delta x equals VI plus VF over 2 times delta t, and there is my second kinematic equation. The nice thing about this particular kinematic equation is that it does not involve acceleration at all. We know it is accelerating because there's a different VI and VF, but it's not actually, we don't see A up here. And I'm going to erase it in just a second, so just know you don't need to write it down. But what you should see when you look at this complicated mess is just this. Hey, delta x equals average velocity times time. Does that make sense? All right. This next part's going to get a little bit ickier. Every other equation is based on these two. Every other equation. From this point, it's going to get pretty heavy in algebra, so feel free to stop me and ask to see something again. Obviously, I am recording this video, so you can look back on it, but I can't tell you how many times in a physics class a professor has done something like what I'm about to do for you, and I ignored it, and then later on, I'm like, holy crap, I have no idea where this came from. I'll just tell you this brief thing and then move on past it, because sometimes you don't even care. If you don't understand how something works, and it takes a trick to do something, you cannot learn anything more complicated than that. Okay? Like, for example, if you don't understand how trig works, but you know how to do it because you know the trick or you use your calculator or whatever, that's great. But if anything is built upon trig, you don't stand a chance of understanding what that thing is. So when I take extra time to go over these, I want you to understand that that's the reason why. Sometimes students get frustrated and they go, Spano, just give me the equation. It's stupid. You could have wrote that at the beginning and saved yourself 20 minutes. Trust me, it's really important for moving forward. To put this in perspective, not to scare you, but to be honest, kinematics is kind of like the ABCs of physics. It's super simple, and we assume it's going on in the background while we're dealing with much more complicated things. So, do you have to know how to do it? Sure. You have to know your ABCs, but also we want to get past it and move it. If you don't fully understand it, then it becomes more difficult moving on. All right, so here's what's going to happen. You should understand that this one up here comes from the definition of acceleration. Let's call this kinematic equation 1. You should understand that a kinematic equation 2 came from the definition of average velocity. And that's really, if you understand those two fundamental ideas, that is the bulk of kind of conceptual stuff, and everything I'm about to do is algebra. So, what I want to do is I want to manipulate this so that I just have a different combination of variables. Right now, if you look at questions 1 and 2, what you'll note is that there are 4 variables in each. What these equations then allow you to do is, okay, that means I need to go find 3 of them, and I can always calculate what the 4th one is. Okay, so if I had VI, A, and delta T, I can get VF. Or down here, if I had VI, T, and delta X, I could get VF through some algebra. So what I'm going to do is I'm going to take 1, and we're going to substitute it into 2. Okay, so VF is nicely already solved for right here. So VF is the exact same thing as this here. So instead of VF, I'm going to substitute this right here. So I'm going to rewrite this equation, delta x equals, and wherever I put parentheses, it's very important when you substitute to help yourself understand it. So plus, in parentheses, I'm also going to write VI plus A delta T, and that's all over 2 times delta T. That's freaking icky. So we're going to simplify it so it's less icky. What is the first thing that I could do to make it less icky? Before you distribute anything, I would even say. Remember, these parentheses is arbitrary just to show that that's there, but technically if you took away those parentheses, what nice simplification could you have? Combine the velocity initials into 2VI. So I'm not going to write the left side because it's not changing, but this should be 2VI plus A delta T all over 2 times delta T. Next step, I don't want to put this, I got a 2 and a 2, and that's stupid in there, so here's what I'm going to do. I'm going to divide everything inside by 2. So that, of course, the left side becomes VI, and the right side has a times delta t over 2, which of course you well know, but just making sure, is the exact same thing as 1/2 out in front. And that's usually how you see this. And the final step, what should I do to simplify? Yeah, let's distribute. So my final equation should be this. Delta x equals vi times delta t plus 1/2 a delta t squared. And this, while probably one of the more complicating looking kinematic equations, that boy right there is going to be your bread and butter. If you're uncomfortable with it, get comfortable with it quick. It's necessary. Also, if any of the kinematic equations make you feel like, oh, that's yuck, whatever, I cannot stress this enough, lean into all of them. You need to know how to use all of them. Now let's talk about why that looks weird. Let's talk about why you already know that makes sense. In the lab, what was your velocity initial? 0. If that term was 0, what does that mathematically, I don't care what delta t is, what does that mathematically do to the first term? Cancels it out. It's gone. Okay? Well, I'm covering up the first term. You can't see it. Okay? If that was your final equation, and I asked you, hey guys, graph delta x versus delta t, what shape should that make? Parabolic. So it's probably a good thing that in your lab, it does. So your lab already told you that this was supposed to be the equation. As a matter of fact, if you did the calculation of the k value already, what you should find about that k value is that it's actually 1/2 your total acceleration. All right, other ones to talk about though real quick. Let's go back to number 1. Hey, if vi is 0, same thing. Wouldn't that cancel this out? And then if I asked you, what should the equation vf versus delta t make? It should make a linear function. So it's probably a pretty darn good thing that it actually does. As a matter of fact, you might note that this particular graph that is right there is literally what, come on, nope, I had it. What I constructed right here when having that discussion about average velocities. This is just instantaneous velocity relative to time. All right, so we've got 3 kinematic equations right now. Okay, we have the one created from acceleration, we have the one created from average velocities, and through a little bit of algebra, we have this guy right here that talks about displacement relative to time. I mentioned that earlier that there are 4 kinematic variables in each, and you'll notice that is the exact same thing here. There are 4. The one that's missing, by the way, there's a total of 5 that we regularly use, is velocity final. Even though t is used twice, yeah, it still is. They only made out of 4 variables. So we got one more to go. There's only one more equation to do. And what we're going to do here to solve for that particular equation, you'll notice last time for equation 3, I kind of substituted 1 into 2. So what I'm going to do is I'm going to substitute 2 back into 3. But the first simple step that I'm going to do is actually, instead of solving, because delta x isn't up here, I'm going to solve this for delta t over here first. Now that's a simple thing. It doesn't maybe look simple. As complicated as this crap is, it's a fraction, which means all I need to do is multiply by the reciprocal of fraction on the right side and the left side. That'll cancel out over here. And on the right side, it'll end up as 2 times delta x all over vi plus vf. It's moves like that one that make me go, hey, you should probably redo this algebra later. And now that I've got t solved for, I'm going to substitute t right here into that equation. So I'm now going to once again rewrite equation 1, but instead of delta t, I'm going to write this whole mess right here. So we have vf is equal to vi plus a. Instead of delta t, I write 2 delta x over vi plus vf. And again, that's icky, and we need to simplify. Let me tell you the key rule of Spainhour's rules for simplification. Okay? If you struggle with icky, messy things such as this, get rid of the fraction first. Easy go-to every single time. The fraction over there on the right side is, of course, 2x. Or actually, I could put a in the middle of that, which I think I will eventually do. I'm going to put a right there in the middle. So down here, let's go 2a delta x. Because again, the parentheses are arbitrary for purposes of looking at substitution. But I got vi plus vf on the bottom. So what am I going to do? I'm going to take vi plus vf and multiply it across the board. Now, I'll tell you right now the mistake that most juniors make with this level of algebra when things get complicated. They do this. They go vi plus vf, boom, boom, and they go vi plus vf, and they stop. What is the problem with that? Not quite. We're not to that part yet. We've made a mistake with the general algebra. Yeah. The problem is that most juniors start to think of algebra as happening on the right side and the left side only. But the thing is, as complicated as this crap is, let's make up some numbers. Let's say this term is 10, and this term is 2, and that term is 8. What the equal side said is the right side and the left side are both equal to 10, right? If I divide everything by 2, okay, well, this is 10 over here on the left side, divided by 2 is 5. And you just took the 8 and divided by 2, and that's 4, but you did nothing to this guy right here. So now you have 5 equals 2 plus 4. Is that accurate? Meaning, there are 3 terms, terms being something that's added. When you do multiplication or division, you must do the same thing to every term. So this term also must get a vi plus vf multiplied in there. Now this guy right there becomes just a real simple like this. And then yes, as was already stated, we now need to distribute, which looks icky, but humor me. Here's what I'm going to get over here. I'm going to get vf squared. I'm going to pick these two first. And then I get a plus vi times vf. And what do I get here? And luckily for us, that looks ickier than we started, but notice what nice simplification happens. What nice simplification will happen here? The vi and vf are on both sides, and thus will cancel left, cancel right, leaving me with the fourth kinematic equation. In the lab, what did we say vi was? 0. Which if that was 0, this equation would become vf squared, come on computer, equals 2a delta x. And then if you wanted to solve for vf, obviously to get it to the first power by itself, what would you do? You'd square both sides. And then that means if you were to graph, theoretically, vf versus delta x, what shape should it make? So it's an awful good thing that on the fourth graph it did, eh? The purpose of the experiment, the purpose of labs, is to show you what real world says it is, even if we don't know the reasoning behind it yet. So that is what you should get. Real quick aside, which is important here, because people do screw this up as well. So obviously, we just said, not obviously, Spainhour should never use the word obviously in here. Sometimes he does, and that feels condescending, and that is wrong, okay? Nothing in this class is obvious. I apologize. But humor me real quick. What should the k value of this function be if you were to graph it? Careful, people get this one wrong. Any guesses? 2a is what people guess. That's the wrong answer. Yes. It's not 0. It is the square root of 2a. Because that is how you can simplify it so that it's the exact same thing, right? So what's multiplied next to the square root of x is the square root of 2a. Simple thing, what should the y-intercept be? 0, which of course is exactly what we do expect in our lab. Questions, concerns about the kinematic equations thus far? Let's make a slide that just has them. And as I have it up here, every year somebody writes down one variable wrong and it haunts them for like 3 assignments because they have no idea why they're getting the wrong answer, but they're using the wrong equation. I'm going to be very, very careful right now, as should you be. So, kinematic equation can sort of be split into 2 camps, but one of the camps is super easy. We spent like no time on it. The first one is, hey, what if acceleration is 0? Well, if acceleration is 0, what do you know? Correct, and therefore velocity is constant. Correct. And under that camp, you can either, like I said, say constant velocity is delta x over delta t, or you can do the rearrangement of that one. I don't care. Pick one and be consistent. Or what if acceleration is not 0? And under that case, what we have is Vf equals Vi plus a delta t. Vf squared equals Vi squared plus 2a delta x. By the way, the reason I went in that wonky order compared to what I did the first time is because you'll note that there are 2 of these equations that begin with Vf and 2 that begin with delta x. My rule on these equations, by the way, somebody asks me every year, they go, do I have to memorize them? I go, you don't have to, but you're gonna, okay? Meaning, you're gonna use these so often, I very much doubt that you don't have them memorized by the end, but don't feel like you need to go out of your way to memorize them to begin with. Have them written down, use them as is necessary. I imagine you're gonna be using, your notebook less and less. Delta x equals Vi plus Vf over 2. That entire quantity is multiplied by time. And delta x equals Vi times delta t plus 1/2 a delta t squared. The most common things forgotten on these equations are this. 1, the squared, right on the end of that equation. And 2, for whatever reason, this delta x right here, most people write down as a delta t. It's probably my handwriting. We'll just go ahead and blame me. I'm fine with that. Now, over the next 2 to 3 days, honestly about the next week, we're going to spend most of our time with these equations using how to wield them. But the general gist is what I said earlier. You'll note that these 4 equations are made out of 5 variables. The 5 variables are Vi, Vf, A, delta t, and delta x. So the general technique is simple. Essentially, if you know 3, you know 4. And actually, you know 5. You can use, this means these equations, you can use them in whatever the heck order you want. Some of you might use this first one and then the third one to get particular values. Somebody else might use entirely different equations or in a different order. And that's fine, and you should get the exact same value within reason for rounding and all that sort of fun jazz. Okay? So like I said, we'll practice with them. There's definitely going to be easier things to do to learn, but just understand that as you kind of get used to using these, it's there's not a right way to do this. Okay? If you talk to 3 different physics teachers on the same problem, you're more than likely going to get 3 different ways to solve the same problem and 3 different disagreements about what the easiest way is to tackle that particular problem. Okay? I'm not going to go too much further right now. Like I said, the very first thing we do tomorrow is start practicing with these. Your homework right now is honestly the main thing that you should work on if you are all caught up is the algebra on these. Okay? I want you to be able to, not the stuff I just did, I want to be able to you to take this equation and say solve for delta t, and you do not use any numbers whatsoever. You move this equation around to solve for delta t. Okay? That is the entire first kinematics algebra assignment. I think basically it's this. Now, okay, heads up. Notice when I say to solve for, Vf is solved for. So I think there is one thing that says, hey, solve for Vf. You're done. Put a box around it, move on. But always start on kinematic equations from the same spot. Don't start from another spot in the algebra, because then you have to memorize 16 equations as opposed to just 4, and that's not going to be easy for anybody. It's way better for you to just do the algebra. Questions, concerns? Give me a 0 to 5 comfort level with today's lesson. Fair enough. Again, main thing to do now, stay caught up on the homework. If you are caught up, do that kinematics algebra.